Let me welcome you to this lecture. We will now begin our discussion on group 13, group 14 and group 15 elements and the chemistry of these elements. And the elements or the chemistry of these elements, that is from group 13, group 14 and group 15, play a major role in human civilization, and they have many applications, and we will mainly focus on the application of these elements and their compounds in different applications, and also we will try to understand the bonding and structure of these compounds during this course. So let us begin our discussion on by starting with group 13 elements. As we know, group 13 there are 5 elements are present. There is boron, and then there is aluminium, then gallium, indium, and there is thallium is the last element of group 13. Now if you look at the electronic configuration, we will see is that the valence cell electronic configuration for boron, we can write it to be 2s1 and 2s2 and 2p1. All of these elements, for all of these elements, there are 3 electrons in the valence shell, and the electronic configuration. Let us write the electronic configuration. So for this aluminium, it is 3s2, 3p1, while for gallium, it is the valence shell also contains, we can write the 10 d electrons, that is 3d10, 4s2, 4p1, and for indium as well, flipped on, this is 4d10, 5s2 and 5p1, and for thallium it is, the noble gas is xenon. So we also have the F electrons, it also has F electrons, so it is 4f14, 5d10, and then 6s2, 6p1. So that is the electronic configuration for thallium. What we see is that for all of these elements, there are 3 ampere electrons, or there are 3 electrons in the valence shell, while there are, in case of gallium, we have electrons are there present in d orbitals, as well as in case of indium also we have electrons in d orbitals, and in case of thallium we have the f orbitals as well as d orbitals are filled before the 6s and 6p orbitals are filled. So this makes a difference in the chemistry of these compounds, and we will of course try to elaborate how this electronic configuration or difference in electronic configuration, valence electronic configuration of these compounds changes the property of these compounds. Now before we go into that, let us also try to summarize the kind of bonds that these elements form. So in case of boron, we can largely classify it to be a non-metal. Boron is a non-metal, while the rest of the elements, that is aluminium, gallium, indium and thallium, are classified as metals. So these are all metals, and at the same time, now what we can see is that the boron universally forms covalent bonds. So no ionic compound of boron is known so far, that is B3 plus ion is not cannot be obtained, and all the compounds of boron, essentially the bonds are formed, boron forms are covalent in nature. Well, in case of the rest of the group 13 elements, that is for aluminum, gallium, indium, and helium, they can form both covalent as well as ionic bonds. As we know that in case of qualitative analysis, we have identified Al3 plus ions, so aluminum forms ionic compounds when in solution, say, and uh, for the rest of the elements as well, for gallium, indium, and helium also, one can get ionic compounds apart from covalent compounds. So both covalent and ionic bonds are formed by these, the heavier group 13 elements except for boron. Now, the kind of oxidation states in these group 13 elements are also different, that one observes are different. So, for example, in case of boron, we always encounter the oxidation state of 3 positive, while for aluminum, one can get both 3 positive as well as 1 positive, that is, but these compounds of aluminum with +1 oxidation state are generally quite unstable. But for gallium, indium, and helium, one can obtain both +1 as well as +3 oxidation states, and both are quite stable for these 3 uh, +1 as well as +3 oxidation states are common. So this difference in oxidation states of lighter elements, which in comparison to heavier elements, can be explained in terms of inert pair effect. So what we can say, what is inert pair effect, is that in case of the heavier elements, the electrons in the s orbital do not participate in bonding, because because in this case of these heavier elements, this, say for example, in this helium, we see that before this 6s orbital, we have this 4f and 5d orbitals are filled, and because of the low these electrons in f and d orbitals can screen the nuclear charge very weakly, and because of that, these s electrons experience stronger nuclear charge, and that is why they do not really participate in, or they do not tend to participate in bonding, and that is the reason why the heavier group 13 elements, or say for example, that is the reason why most of these heavier elements in the main group groups, we see oxidation state of +2 less as compared to heavier lighter elements. In case of boron, we see +3, while in case of helium, we see both +3 and +1 oxidation state and +1 oxidation state. In case of helium, indium, and gallium are pretty stable, and the reason being is the inert pair effect. So we have now summarized the properties of most of the properties of important properties of these group 13 elements. Now we will go and discuss about the size of atoms of these, and how the size changes in these within these group elements of group 13. So as such, if you look at the periodicity, when we study about periodic properties, we know that as we go down the group, the size of atoms should decrease, because as we or size of atoms should increase. Sorry, because because we fill electrons in a higher level, and that is why the size of atoms should increase as we go down the group. Or atomic size, let's not say size of an atom. Atomic radii increases as we go down the group. So this is the general property, a periodic property, that as we go down the group, the size of atoms or atomic radius is expected to increase because we fill electrons in a higher level. Say here it is 2s, but we go to the 3s level when we go from boron to aluminum, and that is why the size of atoms here should increase. But when you look at the experimental data for atomic radius for these elements, you see what we observe is that this trend is not very strictly followed. That is, the size does not necessarily go increases as we go down the group. Of course, when we go from boron to aluminum, so let us try to. So this is atomic radius, and this is boron, aluminum, gallium, indium, and thallium. So if we plot the atomic radius of these elements here, what we expect that as we go from a lighter element to a heavier element, the size is going to increase, and we expect to see this sort of a plot here if when we plot the atomic radius against these elements of increasing atomic number. But that is not the case. So what we observe here is that when we move from boron to aluminum, of course there is an increase in size. So the size does increase when we go from boron to aluminum, but when we go from aluminum to gallium, what we see is that instead of increase, what is expected, there is a decrease in the size of atomic radius. And then when we go from gallium to indium, again there is a more or less, it remains same, or there is a very slight increase. You can look at the numbers that are present in the textbook. But then again, when we go from indium to thallium, there is a slight decrease of a size instead of the expected increase in the atomic radius. So this is quite confusing, that why should the size or atomic radius, it does not increase as expected by normal periodic properties. So this again can be explained with the difference in the electronic configuration of these elements. What we see is that when we go from boron to aluminum, of course, we fill electrons in a higher electronic level, energy level, and that is why the size increases when we move from boron to aluminum. But when we move from aluminum to gallium, of course, we fill electrons from in a higher energy level, that is from 3s to 4s, 4p we move. But then before that, we also fill 10 d electrons in these 5 d orbitals here. So the screening these d orbitals, or electrons in these d orbitals can screen the nuclear charge very weakly, and that is why these 4s and 4p electrons experience a higher nuclear charge as compared to what one would have experienced without these 10d electrons. And that is the reason why the size of atom essentially gets contracted here, and instead of increasing the size, instead of the expected increase in size as we move from aluminum to gallium, there is a slight decrease of the atomic radius. So this decrease in the atomic radius when we go down from aluminum to gallium, or when we go down from any element on the third row to the fourth row, is essentially that happens because of the filling of the 5 d orbitals with 10 electrons here, which essentially cannot or does not screen the nuclear charge effectively. And this effect essentially of which, or defect because of which the size of atomic radius essentially decreases when we move from the elements of third row to the fourth row, is known as d orbital contraction. So then again, when we go from gallium to indium, of course, here also the electronic configuration remains more or less same, because here again we have orbital electrons in d orbital, and then this we have electrons are filled in 5s and 5p orbital here. So there is a slight increase in size from when we move from gallium to indium. So then when we go from indium to thallium, the size again decreases, and this again comes because the electrons in f orbitals are even more less effective in spreading the nuclear charge as compared to electrons in d orbital, and that is why again in this case as well there is a decrease in size as we move from indium to thallium, and this decrease in size can be attributed to f orbital contraction. So this there's a decrease in size because of both the orbital contraction as well as for f orbital contraction. So this explains the difference in atomic radius, or the how the atomic radius in group 13 elements changes. Also, the same trend we can observe uh, in case of the ionization energy of these elements. What we see, as we increase the size of elements, we know atoms, we know that the ionization energy should decrease, and as we go down the group, again we expect that the ionization energy is going to decrease because because of the increase in the atomic radius. But then what we see is that as we go down from boron to aluminum, ionization energy is going to of course decrease. So let us plot ionization energy. So as we go down from boron to aluminum, ionization energy does decrease, but when we move from aluminum to gallium, ionization energy does not decrease as much as you expect, but it increases slightly. And then from gallium to indium, it decreases, and then from indium to thallium, again, it increases slightly. So that is the trend in ionization energy. Again, this particular trend in ionization energy in case of the group 13 elements can be explained with the help of d orbital contraction and f orbital contraction, the way we have done in case of atomic radius. The same way we can explain this trend in ionization energy by using these two attributes, that is the d orbital contraction and f orbital contraction. So we have now summarized most of the periodic properties of these group 13 elements. So let us now look at the historical background of extraction of these elements. As such, the extraction of boron from borax was discovered by Henry Moissan. So he also obtained Nobel Prize in Chemistry for discovering the isolation of elemental fluorine, and he also apparently discovered the extraction of boron, elemental boron, that is high purity elemental boron from borax. So one can start with borax, which is naturally available. That is, borax, formula of borax is and one can take borax and then add acid to it. Borax is basic, and then when it reacts with acid, one can isolate boric acid from here, and this upon heating, boric acid, when we heat it, it gets converted into boron sesquioxide, or one can say boron oxide. So that B2O3, we call it as boron sesquioxide. The sesqui word here means 1.5, because this is for each boron we have 1.5 oxygen, and that is why we call this compound as boron sesquioxide. So that is B2O3. So once you have B2O3, then we can reduce this B2O3 by using a reducing agent, and the reducing agent that was chosen by Henry Moissan was an electropositive metal, that is magnesium. So when you take magnesium, it is going to reduce B2O3 into elemental boron, and MgO is also going to be, say, if we balance the reaction, so it is also going to form magnesium oxide. This particular method of preparation of or extraction of boron essentially gives you 95 to 98% pure boron, and this boron, there is a lot of impurities are also present, and that is why it is one with this amorphous boron. Amorphous in nature, and the impurities that are present in these in the boron that we isolate from by using this Moissan method are some um, metal borides. That is, we will learn about metal borides. So the metal borides or magnesium borides are going to be formed. Metal borides are going to be present, and we will also, of course, learn about metal borides and their applications during this course. So these metal borides essentially are present as impurity in the boron isolated by using this Moissan method. And for preparation of crystalline boron, or it is for preparation of highly pure boron, one needs to use other techniques. That is, one can start with volatile boron compounds. So one can start with BBr3 and then reduce it by using hydrogen. So then what we are going to get is boron. So this is, let's make it 2, and then let's make it 3. Then we have 2B and 6HBr. So here the only solid substance that you are going to obtain is the elemental boron, and rest all the starting materials and the byproduct that is formed here are gaseous in nature, and that is how one can obtain a pure boron in this case. Other methods of preparation of elemental boron of high purity is one can start with boron hydrides, that is B2A6, and then thermal decomposition of these boron hydrides will essentially give us highly pure elemental boron. We will also learn about the chemistry of these boron hydrides here, because boron hydrides essentially helped us understand the chemical bond in a more detailed way, because they show very special kind of bonding which cannot be explained with the help of classical bonding theories, and that is why we will, of course, during this we will discuss about the bonding in boron hydrides. So these are some of the methods for preparation of elemental boron, and the application wise, boron has been used a lot in industry, because we already know from ancient times borax has been used for as an insecticide, as well as borax has been used for preparation or for manufacturing this heat sensitive glass. That is, we know about borosilicate glass. These are resistant to heat and do not break when heated rapidly. At the same time, we also know about this boron carbide that is used in nuclear reactors for slowing down the fusion reaction, because boron carbide has a higher nuclear cross section, and then it can absorb faster moving neutrons in the reactor, and that then thus slow down the fission reaction. Apart from that, we other applications of boron include uh, a- in chemistry as well, also in reactions, in synthetic reaction we use BF3 as a catalyst, and there are other reagents also, starting you're using boron, that is say sodium borohydride or, is used as a reducing agent in organic synthesis, as well as uh, there are other compounds of boron, say aryl boronic acids also, they have found application in CC bone formation reaction. We will discuss about again these applications of boron compounds in more detail in future. So let us now move to the other element, this aluminium, and look at the extraction as well as the application of aluminium. Now, one particular aspect of these boron, aluminium, and these group 13 elements that we did not discuss earlier is about how the name of these elements came up essentially. So when we talk about, when we say boron, this Humphrey Davy essentially uh, named this element boron as boron, and because of its similarity of this of boron with its nearest neighbor in the periodic table, that is carbon. So one can the name boron so when you use borax and carbon, from here essentially the name you will get rid of this AX here and then CARB over here, and then one obtain the name boron. Now aluminium has derived its name from the double salt alum, that is KAlSO4 whole 2. This has been known for quite some time, this alum, and aluminium derived its name from alum. Also, it was used because this alum was used as an astringent in Greek in Greece in earlier times, and it was quite important industrial compound in earlier times. Then also the name gallium came from the name Gallic, which essentially means France, and it was a French chemist who discovered gallium, and that is why he named it as gallium after his own country, that is France. And indium, both of these two elements, that is gallium and indium, were discovered uh, by using spectrophotometry, and indium apparently shows a characteristic blue line in spectrophotometry, and that is why the name indium came up in case of for this particular element. So now let us go back to the extraction of aluminium. The metal aluminium was very expensive till 1886, and in fact it is said that the French Emperor Napoleon used aluminium utensils or only in special purposes. Now in 1886, the price of aluminium, such a discovery was made that the price of aluminium came down drastically, and now it is a very cheap metal that can be used in, and that is used in many applications. Now this was A method for extraction of aluminium was discovered in 1886. It is independently by two young men. Both of them were 22 years old when they discovered this method. Hall is an American chemist, while Herold is a French chemist, and they discovered this process for extraction of, or economic way to for economic method for preparation or extraction of aluminium independently, that is separately. What they did is that so one for extraction of aluminium, one cannot start with a salt of aluminium and then do electrolysis. The reason is when you do, say for example, when you take AlX3 and then an aqueous solution of AlX3 and then do electrolysis to produce aluminium, that is, you reduce aluminium electrochemically to get aluminium metal in an aqueous solution. The hydronium ion that is going to be present in the medium is going to oxidize the aluminium into aluminium 3+ once again. So you one will fail to obtain metallic aluminium by this way. So one needs to start, or one needs to do electrolysis in a non-aqueous medium, and unfortunately all of these aluminium compounds or the aluminium ore that is available, that is bauxite Al2O3, is non-conductive in nature. So what Hall and Herold did is that they added another compound, that is cryolite. The formula for cryolite is NH3AlF6. So when they added cryolite to the to Al2O3, that is obtained from the aluminium ore bauxite. So then it increases the conductivity of the mixture so that electrochemically aluminium 3+ can be reduced to aluminium metal, and at the same time it also reduces the melting temperature of this Al2O3, because otherwise the Al2O3 melts at very high temperature, while when one adds cryolite to this Al2O3, the mixture melts at around 950 degrees Celsius. And so this essentially makes this process more economic, because one needs to waste less amount of energy to melt this mixture and then do electrochemical reduction of Al3+ to aluminium metal. So this is the reason why the price or this discovery of this Hall-Herold method essentially decreased the price of aluminium, and today it is used extensively in the industry. So for example, the aluminium metal is lightweight and ductile, and that is why it is used to make the outer cover of this, say for example, aircrafts or ships, as well as we use it in food cans, and also in making utensils, and also for the purpose of this electricity conducting wires that are outside. They are made of aluminium, because the conductivity of electrical conductivity of aluminium is as good as copper when you compare it with terms of weight, and that is the reason. And so this method, this Hall and Herold method, essentially allowed one to isolate or extract aluminium in a economic way, and this propelled the application of aluminium in many applications. So then, before, of course, this Al2O3 that is obtained from bauxite is reduced to aluminium metal by electrochemical method, the bauxite ore needs to be, or Al2 needs to be, Al2O3 needs to be isolated from bauxite ore in a pure form, and this can be, this is achieved by a process that is known as Bayer process. So you may have already learned about the Bayer process, where one takes the Al2O3 and dissolves it in sodium hydroxide to make sodium aluminate, which is soluble in this caustic soda essentially in NaOH, and then it is separated from the insoluble impurities, and then it is one decreases the pH so that aluminium gets precipitated as AlOH3, decreased pH. And upon calcination of this AlOH3, one obtains pure Al2O3 from bauxite. So this is how the aluminium is extracted from bauxite by first purifying with Bayer process and then by using the Hall-Héroult method. Now the gallium is present in bauxite itself in trace quantities, and gallium is again obtained electrochemically uh, after purifying while obtaining aluminium or while purifying Al2O3 by using the Bayer process. One can obtain also gallium as a byproduct, and gallium also has important application in electronic industry, that is gallium arsenide is an important semiconductor, as well as it can convert electrical energy into light. That is why it is used as a light imaging diode, and it has found application in the display industry. That is why display electronic displays. Then again, if we talk about indium, also indium, there are no particular ores, and instead indium is present in trace quantities in zinc blend as well as in galena, that is lead sulfide, or in zinc sulfide here. There is zinc blend, and it is obtained from these two ores of zinc and lead, while extraction of zinc and lead themselves. So this is how one can do extraction of different elements of group 13, and we have also discussed about application of these elements. And one application of indium that we should know is that this indium tin oxide, or one uh, writes in an abbreviated way, that is ITO, is a very important substance or material in the electronic industry, because this is essentially a transparent conducting material, and that is why it is used in displays in cell phones or in computers nowadays. So that is how these elements, or the compounds of these group 13 elements are important. We have seen several examples or several applications of these uh, compounds from group 13 elements. Of course, we will discuss the chemistry of these group 13 elements in more detail in the next few lectures. We will discuss primarily the chemistry of compounds of boron, and the bonding in these compounds of boron in more detail. So with this, let me uh, conclude this lecture. What we have learned during this lecture is an overview of the elements of group 13, that is boron, aluminium, gallium, indium, and thallium. We have looked at the electronic configuration of these elements, and then also we have looked what kind of bonds are formed by these elements, as well as the kind of oxidation states available in different compounds of these elements. And then we have identified that or we have discussed the trend in the atomic radius, as well as the trend in ionization energy in these group 13 elements, and we have found that because of the difference in the electronic configuration, or because of the presence of electrons in d orbitals as well as in f orbitals in case of heavier group 13 elements, the their properties are different from what we see in case of the lighter elements, or the properties changes in an unexpected way as as compared to what we anticipate from normal periodic properties. Then we discussed about the extraction of these elements, and we have seen the methods of extraction for boron and aluminium mainly, and we have seen how one can obtain both crystalline boron as well as aluminium in highly pure state. We have also discussed about the some of the application of this heavier group 13 element, that is gallium and indium, which are important in electronic industry. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.